Welcome to part 2 of our lesson on applications of prime factors. We're going to look at the prime factorization of perfect squares and perfect cubes. To start out with, let's look at perfect squares. Remember that every perfect square has two square roots, a positive one and a negative one. So for our purposes in this video, we're going to be dealing with the principal square root, which is the positive one. So we can use prime factorization to help us determine whether a number is a perfect square and to help us find the square root. When we do this, what we need to look to see is if the prime factor has a repeat factor, or if it occurs or if it has a set of factors that occurs as a pair. So for the number 9 here, if I factor 9, I have 3 times 3. So I have one set of the factor here and another set there. So in this case, the factor that gets repeated is the number 3. So the square root of 9 is 3. Now let's see how this applies to the number 36. So with the number 36, if I do the prime factorization of it, I have 4 times 9. 4 can be broken down into 2 times 2, and 9 can be broken down into 3 times 3. 2, 2, 3, 3, these are all the prime factors of 36. Now if I list out these factors, 36 equals 2 times 2 times 3 times 3. What I have that repeats, or the pairs that I have that repeats, would be a 2 and a 3. Because I also have another 2 and 3 here. So if I want to find the square root of 36, I would take one set of those repeated prime factors, the 2 and the 3, and multiply them by each other. So 2 times 3 is 6. So the square root of 36 is 6. We can do another one of 49. The factors of 49 are 7 times 7. And what pairs do I have? Well, I have a pair of 7s here. And so since I just have one number, that was a nice easy one. So the square root of 49 equals 7. If I look at 64, I can factor that down into 8 times 8. And each of those 8s can be broken down further. So I can go 2 and 4 on either side. And then that 4 can be broken down into 2 times 2. And then this one, if I'm trying to determine if it's a perfect square or not, I need to look to see if I have any set of factors that repeats. Well, I've got 2 times 2 times 2, and that repeats again here. I've got 2 times 2 times 2. So if I want to find the square root of 64, well, that is going to be one set of that factor. So it's going to be 2 times 2 times 2. 2 times 2 times 2 is 8. And when you're looking at these numbers, you're probably thinking, well, I can also just know that 8 times 8 is 64. And that is a perfect square. But where this becomes really useful is when we have really large numbers. Alright, so here's a large number, 44,100. So let's look to see how we can use this method to determine if this number is a perfect square and to determine the square root. So our first step is to draw a factor tree for this. So 44,100. Because it ends with 100 here, I'm going to take this number and I'm going to divide it by 100. As a way to start with my factoring. So 100, I know I need to multiply that by 441, and then I can take either side and break them down further. 100 is the easier place to start. 100, I know that is 10 times 10, and then 10 times 10, each of those can be broken down into 2 times 5. And then I can go through a similar process on this side. 441, I can break that down into 21 times 21, and then each of those can be broken down into 3 times 7. And then my next step is to check to see, do I have a pair of factors that repeats, or a set of factors that occurs in pairs. 44,100, if I can write down a pair of numbers for it, I'm going to have a pair here and a pair here. So I'm going to search for a set of factors that occurs in a pair. So I've got a 2 here and a 5 and a 7. So I can have 2 times 5 times 7. And then I've also got another one here. I've got 2 and a 5 and a 7. I also forgot about the 3 in the first one. There's a 3 here. So there's a 2, a 5, a 7, and a 3. So each of those pairs within this factor contains the numbers 2, 5, 7, and 3. And I can figure out the square root of this number, 44,100, by multiplying together just one of the pairs. So 2 times 5 times 7 times 3 gives me an answer of 210. And because I have this pair of a set of factors, then it is a perfect squares. Yay. So let's try another one. So again, we're going to use prime factorization to determine if the number is a perfect square, and if it is, we're going to state the square root. So what we need to look to see is if we have a pair that has a set of factors. So first things first, let's do a factor tree. So 1,225, I can divide that by 5 and get 245. 5 is a prime factor, so I can stop there on that side. But 245, I can divide that by 5 again and have an answer 49. 49, I can divide that by 7, and my answer there is 7. So I have prime numbers at the bottom of my factor tree, so that's where I would stop for this one. And what I want to do is see if I have a pair of a set of factors. So I have 1,225. Do I have a pair with a set of factors? So do I have some numbers that I can multiply together that occur in pairs? So I have a 5 here and a 7 here. So that is one portion of my pair, because I have another one here and then another 5 there and another 7 here. That is the pair to that set of factors. So if I want to determine what the square root is of 1,225, what I need to do is multiply together one portion of the pair of the set of factors. So that's going to be 5 times 7. 5 times 7 is 35. So the square root of 1,225 is 35. And because I get a whole number there, we know that it is a perfect square. And also because we have that pair of a set of factors, we also know that it is a perfect square. Let's try a different one. 1 second, I gotta find it. Okay, so with this one, again, first step, draw a factor tree. So, 3,042. It ends with a 2, so my first step is I'm going to divide it by 2 and see what I get. So when I divide it by 2, I get 1,521. I've got 2 on the left side. That's a prime factor. I don't need to go any further. On the right, it ends in a 21, so I'm going to try dividing it by 3. So 3, when I take the number and divide it by 3, I get an answer of 507. 3 is a prime factor. I can't go any further in there, but on the right hand side I can let's try this one, dividing it by 3. And when I have 507 divided by 3, it gives me 169. And then 169, the factors of that would be 13 times 13. So okay, I've got my prime factors of 3042. Now what I need to do is check to see, do I have a set of factors that occurs in pairs? So I'm going to draw my lovely little brackets here. So I want to see if I have a set of factors that I can put in there where I have a pair. So I've got a 2 here. I've got a 2. And do I have another 2 anywhere else to put here? I don't. Let's check the other ones. I have a 3 here and a 3 here, so I could put a 3 on this side and a 3 on this side. And I've got a 13 and a 13, so I could put a 13 here and a 13 here. Sorry about my pen, I gotta switch it. But because I don't have a 2 to put in this spot, that means that it is not a perfect square. So what you need to have is a pair of a set of factors. In this case, I'm missing a 2, so it's not a perfect square. All right, let's move on. So we can use the same principle to look at the prime factorization of a perfect cube. But let's remember, what is a perfect cube? Well, a perfect cube is the answer we get when we take a number that's the same number and multiply it by each other 3 times. So our example would be 3 times 3 times 3. So your answer there would be 27. We can also write that as 3 to the power of 3, which would be 27. And if I want to find the cube root of something, what you're doing is you're asking yourself, what number that is identical can I multiply by itself 3 times and get the number that's underneath the square root sign? So for this one, again, it's an inverse operation, so it would be 3, because 3 times 3 times 3 is 27. So that's one way you can go about finding the cube root and finding a perfect cube. But once our numbers start to get bigger, this becomes more difficult. So we can use this process of finding a prime factor in order to make it easier. So let's start simple and work our way to more complex. So we can look at this number 27. Let's start with finding the prime factors of 27. I've got 3 times 9. 9 can be broken down into 3 times 3. Now what's different about when we are trying to determine if something's a cube root or not, what we need to recognize is that the prime factorization of a perfect cube will involve sets of factors that occur 3 times. That occur or in multiples of 3. So for the example we've got here, I've got 3. 3 occurs 3 times. So if I'm thinking about the square root of 27, that's going to be 3 times 3 times 3. But because I've got 3 3's, the factor that I'm saying occurs a multiple of 3 is just a 3 here. So the square root of 27 is 3. Let's look at a more complex example. So I've got 216. Let's start with drawing a factor tree for it. 216 divided by 6 is 36. If I go on the left-hand side, 6 can be divided by 2 to get 3. Moving over to the right, 36 can be divided by 6 to get 6. And each of those 6's can be broken out into 2 times 3. So with this one, let's look at our factors that we have. At this point, I have prime factors all on the bottom. They're prime numbers. But let's see if I have any sets of factors that occur in 3's. So I'm looking for sets of factors that occur in 3's. So I've got 2 times 2 times 2, and I've got 3 times 3 times 3. But another way that we can write this is that, we're looking for, sets of multiples that occur 3 times. Well, I've got 2 and 3 here, so I can have 2 times 3. I can multiply that times 2 times 3, and then I've got 2 times 3 here. So if I want to find the cube root of 216, I have to take just one of these portions and multiply it together. So that's going to be 2 times 3, which equals 6. And if you were to plug that back into your calculator, you would have 6 times 6, which would be 36. And then if I take 36 times 6 again, I would get the answer of 216. So we know that that works. All right, let's try another example. So now I've got, again, a bigger number. So 3,375. If I want to use prime factorization to find the cube root of this, I need to first start with drawing a factor tree. So this number ends with a 5, so I'm going to start with dividing this number by, I could do 5, but it also ends in a 75, and I know 75 I can divide by 25. So if I do 25 here, 3,375 divided by 25 gives me 135. 25 can be broken down into 5 times 5. 135 can be broken down into 5 times 27. 27 can be broken down into 3 times 9. And 9 can be broken down into 3 times 3. So now I'm going to use my trick to see if I have any sets of 3, any sets of factors that occur 3 times. Well, we have a 5 here and a 3 here. So I can have 5 times 3. I've got a 5 here and a 3 here. So that could be another 5 times 3. And I've got a 5 here and a 3 here. So that can be another 5 times 3. So when I'm looking at the cube root here, I can take one portion of that and multiply it together. So I have 5 times 3 is equal to 15. So the cube root of 3,375 is equal to 15. All right, let's do one more set of examples where we're looking to see if this is a cube root and if it's a perfect cube. So our first step is always to draw the prime factorization. So this time, let's do a division table. So let's start with, this ends in a 2, 6,912. It ends in a 2, so let's divide this by 2. So if I divide that by 2, I get 3,456. I divide that by 2, I get 1,728. Divide that by 2, I have 864. And we're going to keep going. 864 divided by 2 is 432. If I divide that by 2, it's 216. Still going to keep going. 216 divided by 2 is 108. Again, I can still use 2. 108 divided by, you guessed it, 2 gives me 54, getting smaller. 54 divided by 2 is 27, but I can't use 2 anymore here because 27 is an odd number, so I can't divide that by 2 and get a whole number. So I'm going to choose 3. So I have 3. 27 divided by 3 gives me 9. 9 divided by 3 gives me 3. 3 divided by 3 gives me 1. Once I get to 1, I can stop my factorization. Okay, let's keep going. So now what I want to see is that, do I have a set of factors that occurs 3 times? So I'm going to draw my 3 little brackets that I can put my sets of factors in. So let's change a color here and see what we can find. So I can go 2, put a 2 in here. I have another 2 here, so I'm going to put this 2 here. Third 2 there, so that's my first number in my set of factors. And I'm going to keep working my way down here. So I've got this other 2. I'm going to put that as a second 2 in my set. I've got another one there. Got another one here. All right, so let's keep moving. I've got another 2 here, so I'm going to put this into this set of factors. That was that one. Another 2 here that I'm going to put into the second set of factors. But when I look for another one, there's not another 2, so I'm actually missing a 2 here. But let's finish up to see if we can add anything else. I have a 3 here, so I can put a 3 in this set of factors. Got another one here, and I've got another one here. But are all of these sets of factors the same? No, it's missing a 2 here. And since it's missing a 2, that means that it's not a perfect cube. All right, one last example. So we have an even bigger number here, and we want to decide if it is a perfect cube and what the square root of it is. So I have 970,299. So let's start with drawing a division table for it. Sometimes we can draw our division table slightly different and just kind of draw a little box underneath it. So this number ends in a 9, so I'm going to choose a prime number to divide it by of 3, because I know 3 goes into 9. If I take this number and I divide it by 3, I get 323,433. Again, this number ends in a 3, so I'm going to choose a 3 to divide it by. All right, when I get that, I get 107,811. I've been on a roll with 3, so I'm going to try that again. Divide that by 3, I get 35,937. This divided by 3, I get 11,979. Divide that by 3, I get 3,993. I divide this by 3, I get 1,331. But then that can't actually be divided by 3. So I've done some pre-work on this. If I look at this, I can actually divide it by 11. So this number divided by 11 gives me 121. 121 divided by 11 gives me 11. And 11 divided by 11 gives me 1. So now I have all the prime factors of this number. So my next step is to see if I have a set of factors that occurs in 3s that I can group together and then multiply together. So let's take a look at it here, and we'll just work our way down. So I'm going to start with this first 3. So I've got a 3, I'm going to put that in my first one. I've got another 3, I'm going to put that in my second one, and another 3, I'm going to put that in my third one. All right. I've got another 3 here, so I'm going to put that in my first one. This 3 I'm going to put in my second one, and this 3 I'm going to put in my third set. And let's look to see if we have another set of 3s. Well, I've got not 3, but I have 11. So I can go put 11 in my first set here. I've got another 11 there, so I can put an 11 there, and another 11 there, so I can put an 11 there. Now with this one, all 3 of these sets of factors match. And because they match. Yay. Or they match. So because they match, I know that it is a perfect cube. And if I want to figure out what the answer is to the perfect cube, I can take one of those sets and multiply them together. So I can go 3 times 3 times 11 would give me an answer of 99. So the cube root of 970,299, cubed root of it, is 99. Wonderful work, guys. Thank you for working with me to get through that. Check the classroom for the questions I'd like you to do from the workbook, and we'll see you in the next class.